Let's continue now. In the last video, we looked at prime ideals in a ring. These are ideals where if a product of two elements belongs to the ideal, one of the elements belongs to the ideal. So let's now continue. So I'm going to define an important class of rings now. So this is the definition that I will give now. So let R be a ring. So R is a ring. So R is called an integral domain. So these are important class, this is an important class of rings. R is called an integral domain if the following property holds. A, B in R, if A times B is 0, A, B means A times B is 0, that implies that A is 0 or B is 0. So if you have, so simply put, it says that if you have two elements in the ring whose product is 0, one of them must be 0. This is a very familiar property for us. For example, integers have this property. So immediate example, the most obvious example is Z is an integral domain. This is because if you multiply two integers and you get 0, one of the integers must be 0. If both are non-zero, their product is also non-zero. So Z is an integral domain. This is easy. And in fact, this also suggests to you that this is related to the definition of prime ideal. There it was an ideal I is called prime if AB is in I, implies A is in I or B is in I. Here, instead of asking for AB in I, we are saying AB is equal to 0. In other words, it is a statement about the 0 ideal. So it's a simple exercise to verify that R is an integral domain. R is an integral domain if and only if the 0 ideal is prime. Okay, this is a very simple exercise that I will not do, I will let you work it out, because if it's an integral domain, you take the 0 ideal. If product of two elements is in the 0 ideal, that means product of those two elements is 0, because it's an integral domain, one of them is 0. So one of them must be in the 0 ideal. Similarly, if it's a 0 ideal is prime, then you can show that R is an integral domain. An equally simple exercise is that I, so let R be any ring and I is an ideal of R, let I be an ideal of R. Then we have the following equivalence. So then we can say I is prime if and only if R mod I is an integral domain. So this is a characterization of prime ideals. In fact, it is sometimes useful to verify that ideals are prime using this condition. So I is prime if and only if R mod I is an integral domain. So this follows because of our understanding of quotient rings and correspondence ideal of theorem and so on. So I will quickly tell you why this is true. Why is this true? So why is this statement that if I is prime if and only if R mod I is an integral domain true? So suppose I is prime. So in this direction, suppose I is prime. So let's take two elements. What are two elements of R mod I? They are of the form R mod A bar comma B bar. So suppose A bar times B bar is 0 bar. Right? So remember, in order to verify that a ring is an integral domain, we have to check that product of two things is 0 implies one of them is 0. So I'm taking two things whose product is 0. But that means, remember, A bar B bar is just A bar AB whole bar. This implies, by the definition of a quotient ring, if an element is 0 modulo I, that means that element is in I. But since I is prime, that is the assumption. If I is prime and AB is in I, A is in I or B is in I. But if A is in I or B is in I, that means A bar is 0 or B bar is 0, which is exactly the statement for an integral domain. So if I is prime, R mod I is an integral domain. Conversely, if R mod I is integral domain, you want to show that I is prime. So take two elements whose product is in I but then take the residue. So I will leave that as an exercise similar to the above. Okay, so I will leave it as an exercise. It's a good exercise for you to get used to the notion of quotient ring. So in other words, to verify that an ideal is prime or not, it suffices to show that, verify that R mod I is an integral domain or not. So now some examples I will consider before moving on to maximal ideals. So suppose R is an integral domain. So okay, so as I told you earlier, Z is an integral domain. Another example would be Z mod 2Z. This is an integral domain, this is an integral domain. What about Z mod 4Z? This is not an integral domain. Let's see why. Not an integral domain. Why? So why is this? Can you produce two elements in this ring whose product is 0 but neither element is 0? Yes, you can do that, because 2 bar times 2 bar is 4 bar equals 0 bar in Z mod 4Z, but 2 bar is not 0 bar. Okay, so this is another reason is that we already saw in the last video, 0 bar is not a prime ideal of 4 bar Z mod 4Z. Right? 0 bar is not a prime ideal, hence Z mod 4Z is not a prime ideal by the observation I made here. R is an integral domain if and only if 0 ideal is prime ideal. Yet another way to see this is the following. 4Z, sorry, I should not put brackets. 4Z is not a prime ideal of Z. That also we know, because product of 2 with itself is in 4Z, but 2 is not in 4Z. So 4Z is not a prime ideal of Z, and hence by the exercise I left for you, Z mod 4Z cannot be an integral domain. So as you can see, all these are connected, the notion of prime ideal and the notion of integral domain. So some other examples. So fourth example, if R is an integral domain, so let's say R is an arbitrary integral domain, then I claim that the polynomial ring in one variable, or in fact any number of variables over R, is an integral domain. So this requires a little bit of work, but it's not difficult at all. How do you show that Rx is an integral domain? You want to show that any two polynomials if you take that are non-zero. So we want to prove that. So if fx and gx are in Rx, let's say fx is non-zero, gx is non-zero, then fx times gx is non-zero. So this is the contrapositive statement for definition of integral domain. You take two elements which are both non-zero, their product is non-zero. This is not difficult now to show, because, so I'll leave the details for you. If fx is a non-zero polynomial, write it as an xn plus whatever, I don't care what the remaining terms are. And similarly gx is bn xn, bm I will write, and I don't care. And I know that an is non-zero, an is an element of the ring of course, bm is non-zero, bm is in R. Because f and g are non-zero polynomials, their leading coefficients we will take to be non-zero. We will take the largest coefficient. So the degree of f is n, the degree of g is m. So by definition, these are non-zero. But because R is an integral domain, R is an integral domain implies an times bm is non-zero. Because an and bm are non-zero elements, their product cannot be 0. Now what is fx times gx? The point is fx times gx, you will have to multiply two polynomials, so there will be lots of terms. But there will be exactly one term with degree n plus m. So these are lower degree terms, which I don't care about. Right? The largest power of x that you can find in the product of f and g is n plus m. The contribution coming from ANXN, BMXM. So when you take their product, you will have this. For every other term, the degree will be strictly less than n plus m. So they are lower degree terms. Now, because AN and BM are non-zero elements in the ring, AN BM is non-zero, so hence this is non-zero. And there can nothing else, no subsequent term of the product can cancel this. So this will survive and this is non-zero. Okay. So this proves that product of two non-zero elements in the polynomial ring is non-zero. And the crucial statement is this. You need that A and BM is non-zero. So R is in integral domain is of course important. So if not, then Rx can't be in integral domain. That is because R sits inside Rx. So as an easy example, so I'll say that if R is an integral domain, another example which is related to my remark just now that I made, if R is an integral domain and let's say R prime is a subring of R. R prime is a subring of R. That means remember that it's a subset which is closed under addition, multiplication, and it is in fact an abelian group under addition and so on. So it's by itself as a ring. Then R prime is also an integral domain. R prime is an integral domain. That is clear, right? Because if two elements you take from R prime, their product is 0. Those two elements are in fact in R. And their product of course is the same. That is the nature of subring. The product of R prime is same as product of R. So if two elements of R prime are multiplied, you get 0, then their product in R is 0. Because R is an integral domain, one of them is 0. So you conclude that R prime is an integral domain. So this is easy. On the other hand, if you take an integral domain and a bigger ring, then you don't always get an integral domain. So consider in this case R to be Zx modulo the ideal x squared. So I claim that this is not an integral domain. Why is this? So let's check this. So I claim that the ring quotient ring Zx by x squared is not an integral domain. So in this case it's trivial because consider the residue of x. So consider x bar in R. Then x bar is non-zero. Why is this? X bar is non-zero because x is not in the ideal x squared. This is the reason. Remember, elements residues are 0 if before taking the residue the element is in the ideal that you are quotienting. X bar is 0 if and only if x is in the ideal that you are quotienting, which is x squared. But certainly x is not an x squared because x is ideal generated by x squared is a collection of elements which are multiples of x squared. In particular, if you take a non-zero element in the ideal x squared, its degree will be at least 2, whereas x has degree 1. So x can't be in x squared. So it's non-zero. But what about x bar squared? X bar squared is x squared barred. But x squared bar is 0 because x squared is in the ideal x squared. So you have a non-zero element x bar whose product with itself is 0 bar. So our Zx mod x squared is not an integral domain. In other words, the 0 ideal of this is not a prime ideal. But remember, Zx, Z can be thought of as sitting inside Zx mod x squared because any integer is a polynomial, right? It's a constant polynomial. So you can take that as an element of this. So in other words, to be more precise, what I am saying is the natural map. So we have natural maps Z to Zx, which is simply the inclusion of Z in, so an integer n goes to an integer n. we have also a natural map coming from the quotienting process. So this here, so here of course fx goes to fx bar, the second map. So this is composition that you have is an injective map. Remember that once you have so this is an injective map because an integer is never inside, a non-zero integer is never inside the ideal x squared, because if n goes to 0, if n bar, so the reason is if n bar is 0 bar in zx mod x squared, that means n is in the ideal generated by x squared, but the only integer that's in the ideal generated by x squared is 0. So the kernel is 0, that means it's an injective map. Once it's an injective map, z is isomorphic to its image by the first isomorphism theorem. So you can think of z as a subring of zx mod x squared. Z is an integral domain, but zx mod x squared is not an integral domain. So subrings of integral domains are integral domains, but if a bigger ring containing an integral domain is not necessarily an integral domain. So these are some examples of integral domains. This notion of integral domain is intimately connected to the notion of prime ideals. So the next class of rings that I am going to study, so ideals that I am going to study, is the very important notion of maximal ideals. So let me define these now. So I am going to define maximal ideals. So let R be any ring and let I be an ideal of R. So let R be a ring, let I be an ideal in that ring R. We say that I is a maximal ideal or I is maximal if it's a maximal ideal. So there is no bigger ideal, okay, but there is always one bigger ideal. If I is a proper ideal, you can always consider R as an ideal that's bigger than I, but that's a trivial case, so we don't want to consider that. So maximal except for the full ideal. So I is a maximal ideal. So the one way to put this is I is maximal ideal if you have J is any ideal. So first of all, we need two conditions. One is that I is a proper ideal. So remember, also prime ideals are supposed to be proper. Similarly, maximal ideals are supposed to be proper. That means I is not equal to R, right? So proper ideal means I is not equal to R. The second condition is I, if J is any ideal such that I is contained in J, which is contained in R of course, then either I is J or J is R. Okay, so the only ideal that contains I, the only ideals that contain I are the ideal itself and the ring itself. So these are the only two ideals that contain I. Otherwise it's maximal. So there is nothing properly between I and R. So that's a maximal ideal. So I want to make some obvious comments here. The first comment is, so it's an example. Consider the ring of integers. This is our most familiar example, right? For everything we start with the ring of integers. So what are maximal ideals? So take any ideal, let I be an ideal. So we know that any ideal of Z can be written as nz for a non-negative integer n. So if you remember from the last video, we started with this and determined when it is prime. Now we are going to determine when it's maximal. So let's take I equal to nz and determine when, under what conditions on n is I maximal. So first consider n equal to 0. This is the obvious case, first case. So unlike the case of prime ideal where 0 ideal was turned out to be prime, here it is not maximal. The 0 ideal is clearly not maximal, right? Why is this? Because 0 ideal, for example, is contained in 2z. Contained in z, and 2z is not equal to 0, 2z is not equal to z. So there is an ideal which is strictly bigger than 0 and which is strictly smaller than z. So it's not proper. So it's not maximal. Now suppose on the other hand, just some initial examples, n equal to 1. Then we have the ideal generated by 1, which is z. Of course, by definition, this is not maximal. Maximal ideals are proper ideals. What about n equal to 2? 2z. Now this is interesting. So let's see. Is 2z maximal? So let's suppose that 2z is contained in j, contained in z. And suppose that j is not equal to 2. If it is equal to 2, then of course we don't get any information. Suppose it's not equal to 2z. Then that means j contains an odd integer. So j contains an odd integer, say n, let's say a. So because j is not equal to 2z, remember 2z contains the set of all even integers. If j doesn't contain an odd integer, j would be equal to 2z, because j contains 2z. Only way that it can be strictly bigger than 2z is if it contains an odd integer. Let's call it a. But then we can write 1, for example, a minus 1 is in 2z. Because a is odd, a minus 1 is even, every even integer is in 2z. So a is in, but 2z remember is contained in j. This implies a is in j and a minus 1 is in j. A is in j by hypothesis, a minus 1 is in j because a minus 1 is an even integer. So now if a minus 1 and a are both in j, this means that a minus 1 is in j. That means 1 is in j. That means j is z. Right? If two consecutive integers are in j, the difference which is 1 is in j, but j is in, then j is the unit ideal. Now that proves that any ideal that contains 2z properly is the full ring. That means 2z is maximal. Right? Because that is the definition of a maximal ideal. If you take any ideal that contains 2z and that ideal is not 2z, we showed that that ideal is the full ring Z. So it's a maximal ideal. What about n equal to 3? Similar reasoning as above. Shows that 3z is also maximal. Okay, if an ideal contains 3z properly, that means it contains an integer that's not a multiple of 3 by definition. Using that and a multiple of 3, you can write 1 as a linear combination. So that's exactly the reason that we used in the case n equal to 2. What about n equal to 4? 4z is not maximal if you think about it for a minute. It's not a maximal ideal. Why is that? Since 4z is contained in 2z, which is contained in z, this is proper, this is proper. Right? 2z means all even integers, 4z means all multiples of 4. Certainly every multiple of 4 is even, so 4z is contained in 2z. But 2z contains 2, 4z does not contain 2, so this is a strictly bigger ideal. And 2z of course is not the entire ring, so there is something strictly in between 4z and z. So this is a not a maximal ideal. And more generally, this is an exercise for you. Nz is maximal if and only if n is prime. Okay, so I will let you do this. I am going to do another proposition soon, which will also prove this. But this you can directly show also. Nz is maximal if and only if n is prime. Remember in the examples that we have done, 2 and 3 happen to be maximal, 4 is not maximal. And that's because 2 and 3 are prime, 4 is not prime. So Nz is maximal if and only if n is prime. So if you compare prime ideals and maximal ideals in Z, recall prime ideals of Z are 0 and nz where n is prime, right? There was this additional prime ideal. 0 is a prime ideal of Z. What are maximal ideals of Z, which we just computed by this exercise? So this is an exercise for you. What are maximal ideals of Z? These are just nz. So every maximal ideal is in fact a prime ideal, but there is a prime ideal that's not a maximal ideal. And so that is not an accident. In general, we have the following proposition. In any ring, let R be a ring, every maximal ideal of R is prime. So a maximal ideal is automatically prime. We know that the prime ideals are not maximal because the 0 ideal of the integers is prime, because product of two integers is 0 means one of them is 0, but 0 ideal of Z is not maximal because the ideal 2Z contains 0Z properly and 2Z is a proper ideal. So prime ideals are not always maximal. However, maximal ideals are always proper. So what is the proof? So let I be a maximal ideal of R. So let I be a maximal ideal of R. So I want to show that I is prime. So definition of remember prime means if a product of two elements is in I, one of them is in I. So let A comma B be elements of the ring R such that AB is in I. We will want to prove at the end of the proof that either A is in I or B is in I. So suppose that if possible A is not in I. So if A is in I, we are done because we are trying to show one of them is in I. If A is in I, we are done. If A is not in I, we will show that in fact B is in I then. So suppose A is not in I. Then consider the ideal J defined to be I plus A. If you remember, I have defined ideal sums earlier in a previous video, but to recall that these are all elements of the form X plus AR, where X is in I and R is in R. Okay, this is a simple description of elements, but in general, if I and J are two ideals, I plus J is just R plus S, or let's say A plus B. A is in I, B is in J. This turns out to be an ideal in fact. If you remember this, that's good. Otherwise, please do this exercise. If you have two ideals, their sum is an ideal. So in this case, you take any element of I and any element of the ideal generated by A, which is of the form AR, because the ideal generated by A is of the form elements of the form AR, R in R. Now, this clearly is an ideal containing I, right? Because certainly you can take R to be 0. If X is in I, X plus 0 is in I plus A. So X is in J. Certainly I contains J. And also I not equal to J. This last point is because A is in J, but A is not in I by hypothesis. Remember, A is in J because you can take X to be 0 and R to be 1. That means 0 plus A is in J. So remember, in general, if you take two ideals and their sum, it's a bigger ideal. It's an ideal that is generated by both of them. So it contains both of them. So J is the ideal generated by I and A. So it contains A, but by hypothesis, A is not in I. So J is an ideal which is strictly bigger than I. But what do we know about I? I is maximal by hypothesis, right? We have started with a maximal ideal. I is a maximal ideal which we are trying to show is prime. So I is maximal means there can't be any ideal between I and R properly. So J is equal to R. J is properly bigger than I. So J must be the entire ring R. That means 1 is in R always, which is J. That means 1 is in J. So J can be written as something of this form. So there exists X in I, R in R, such that 1 is equal to X plus AR, right? Because every element of J is of the form X plus AR, where X is an element of I, R is an element of the ring. We concluded that 1 is an element of R, hence 1 is an element of J. So there exist elements X and R such that X plus AR is equal to 1. But now let's look at this and multiply both sides by B. B is our other element. So we get B is equal to Bx plus ABR, right? B times 1 is B, Bx plus BAR. This is the distributivity of addition and multiplication. But X is in R, sorry, so now let's look at some obvious implications. X is in R, sorry, X is in I in fact, right, because X is in I. X is in I implies Bx is in I. If X is in I, Bx is in I, correct? Because I is an ideal, you multiply anything by arbitrary ring element. We don't need anything about B here. B is any ring element, Bx is in I. And also by hypothesis, AB is in I, because we have taken two elements whose product is in I. So ABR is in I. So Bx is in I, ABR is in I, though hence their sum is in I. Right? Bx is an element of I, ABR is an element of I, their sum is in I. But what is this sum? This is exactly B. B is Bx plus ABR. This means B is in I. So I is prime. So what we have shown is, if I is a maximal ideal and two elements in the ring have the property that their product is in I, one of them must be in I. So I is prime. So this completes the proof. Now if you go back to the exercise that I gave you, where I asked you to show that an ideal nz of the integers is maximal if and only if n is prime. This is now clear, because if it's maximal, okay, so one direction of it is clear at least. If it's maximal, then it's prime. So, and it cannot be, n cannot be 0, so n must be prime. On the other hand, if n is prime, you have to show that it's maximal. So that part is an exercise for you. Okay, so let me stop this video here. In this video, we looked at the notion of integral domains and we started talking about maximal ideals. We characterized maximal ideals of the integers, and we also proved that any maximal ideal is a prime ideal. Thank you.